Hello, everyone. My name is Ron Polidan. I work for Lunar Resources. I'm the principal investigator for the NIAC Phase 1 study of FarView, an in-situ manufactured lunar farside radio observatory. This chart lists my collaborators, my team members. In addition, we have a large number of collaborators across the country helping us with some of the science, some of the robotics, some of the rovers and such. Our study is going very well. We've made substantial progress in all the critical areas and have removed a lot of issues that were causing us problems at the beginning. There are no showstopper issues that have been found, and FarView is actually looking more feasible and more implementable than it did at the time of our Phase 1 proposal. Next chart, please. So what is FarView? Before I actually get into the details, I want to remind everybody that this is a Phase 1 study, so we don't have a whole lot of money, and we're only 40% of the way through the study. So all the information I'm going to be presenting today should be considered very preliminary. Our concept has evolved dramatically over the past few months and will continue to evolve as we flesh out some of the technical details of the study. But FarView is a low frequency, 5 to 40 megahertz radio telescope array. Actually, it's a radio interferometer comprised of 100,000 dipoles distributed over 120 square miles or 120 square kilometers of lunar surface. The observatory is manufactured in situ, utilizing Lunar Resources developed technologies that first extract metals and oxygen from the lunar regolith and then manufacture functional products from those metals. FarView needs to be built on the lunar far side to shield it from Earth's ionospheric and anthropomorphic radio interference that make these observations difficult to do from the Earth. This study is more of a system study than a technology study. We are attempting to define an implementable architecture along with the necessary technologies needed to build this observatory. The technologies themselves are being developed through ongoing funded programs from NASA, NSF, and other agencies. So this study is intended to really just develop and mature the new approaches, concepts, and technologies to extract the metals from the lunar regolith and manufacture from these extracted materials using robotic systems almost all of the materials needed for FarView, including the antennas and the power infrastructure. So why is this important? Well, on the science side, the observations that FarView will make will provide unprecedented insight on the earliest stages of the universe, testing cosmological models. But it will also provide information on solar and solar system magnetic phenomena and may be able to detect magnetic activity in nearby exoplanet systems. But we think the biggest impact will be advancing concepts for in-situ resource extraction and for the manufacture of products utilizing lunar regolith. This advancement will have a very broad impact on how we approach building scientific and exploration facilities on the moon, in particular, developing processes and techniques to build in-situ solar arrays and batteries. Because the one thing everybody will need on the moon is power. Next chart, please. So a little bit on the science. The large number of dipoles, along with the huge size of the observatory and the lunar farside site are all required because FarView's primary science is to probe the pre-stellar dark ages, when the universe was filled with neutral hydrogen and the first stars had yet to form, through to the cosmic dawn when the first stars and galaxies began forming. What we are observing is the 21 centimeter line of neutral hydrogen redshifted into this low frequency band. It's a very faint signal, so we have to really reduce all background noise. Foreground is always going to be there, and that is going to be a big effort of data analysis. But if we can eliminate the Earth's noise source, these observations now become viable and possible with something like FarView. The figure on this chart, for those who aren't familiar with the ages of the epochs of the universe, places the dark ages and the cosmic dawn into perspective with the rest of the universe, indicating what's happening in each epoch, and it also identifies with the little red arrows there the domain where FarView will explore. The key thing to remember is that FarView is a radio interferometer. As an interferometer, it can map the range of spectral and spatial distributions that are necessary to construct a 3D power spectrum map of the dark ages neutral hydrogen. This contains much more information on new physics and what's going on in that stage than we would get from a single antenna. So that was our reason to go with this very large interferometer. FarView observations will actually be done during both lunar day and night. We actually image the entire sky above the horizon every few minutes. The cosmology observations will be done only at night, only at lunar night for the low background. But all the other science can be done during the day as long as their signal is obviously well above the background. So this includes coronal mass ejections, magnetic activity on Jupiter, Saturn, Uranus, Neptune, other things on there. But also, since we image the entire sky, we're hoping to detect some exoplanet systems, and we will almost certainly see a lot of radio transits. So this will open up a whole bunch of new areas of science. All right, next chart, please. So how do we do this? Well, FarView is enabled by two Lunar Resources developed technologies: molten regolith electrolysis and vacuum vapor deposition. The extraction of materials from the lunar regolith uses the molten regolith electrolysis process to convert raw lunar regolith into metals and oxygen, and then refine them into a high level of purity. This process needs only electrical energy and gravity. No reagents from the Earth, nor any beneficiation of the regolith is required. Our MRE technology is currently being developed through NASA and NSF funding, and it's currently at TRL3. If our programs are successful, it will be TRL5 by the end of those funded programs. But a variant of our MRE technology is actually being used commercially to make steel. So we know the process works. The issue is how to migrate it to the moon. If you want estimates of our production rates, these are very uncertain, but in a year, we expect to generate somewhere around 5 tons of aluminum, 3 tons of magnesium, 4 tons of silicon, 14 tons of iron, and a lot of oxygen from the regolith. Process of manufacturing the dipoles on the lunar surface use our vacuum vapor deposition technique. This is actually a mature technology. It was flown on the Wake Shield facility missions that NASA flew in the 90s and is at TRL-8. It's had to be obviously redesigned for our lunar applications, and we're now at TRL5. It's been tested in the lab and are starting to move on to more environmental tests. This process takes the materials extracted from the MRE and actually manufactures the dipole antennas and power cabling directly on the lunar surface. Modified versions of this vapor deposition hardware are also used to manufacture solar arrays and batteries on the lunar surface using some lunar materials, but some materials bought from Earth. The one other advantage of this is the technologies are very flexible, resilient, and adaptable. So our system can evolve as we learn more about science needs, as we mature the technology, and as we develop a better understanding of the lunar environment. Next chart, please. So I'd like to talk to you a little bit about the architecture. Architecture should be very familiar to people who do radio astronomy from large arrays on the Earth, because it'll be composed somewhere between 150 and 200 subarray antenna elements, each containing between 500 and 650 dipoles, distributed across this 120 square kilometer area on the lunar far side, in sort of a core halo structure. The architecture is fairly similar to that of large Earth-based radio telescopes, and the picture in the upper right shows you a notional distribution of the subarrays at the crater Polidan on the lunar far side. The reason we went to this is that each subarray occupies an area of less than 0.18 square kilometers on the lunar surface. An examination of lunar maps has shown us that finding areas that small that are smooth enough for FarView to deposit its antennas should be relatively easy. So how will construction begin? We're going to start by landing, obviously, our regolith processing facility, which consists of an MRE extraction unit, a refiner cell, and an oxygen capture system, and multiple manufacturing rovers. The first day, we will simply deploy and build a power infrastructure for the RPF. On the second lunar day, the RPF will be activated and start producing metals. The RPF and all the manufacturing operations will be done only during lunar days, stopping production at lunar night. The RPF's thermal design allows it to survive lunar night without external assistance, and it can be used to assist other assets to survive the cold lunar night. From the third day forward, we'll be manufacturing subarrays. Construction rovers will transport extracted metal to the build sites to manufacture the subarrays. In parallel, solar array and battery construction rovers will visit each subarray site and build the necessary power infrastructure for each subarray. Since each subarray is independent, science data gathering will commence as soon as the first subarrays are built and powered, growing as more subarrays come online. Data will wirelessly flow from the antennas to the central data processing system on the landers and eventually be transmitted back to Earth. Since FarView is built of lunar materials, servicing and maintenance of the observatory are relatively easy. With this capability and an occasional replenishment of complicated hardware from the Earth, FarView could actually operate for over 50 years. Next chart, please. So what about beyond the moon? Moving past the moon, our resource extraction technology will also work on Mars. As I said before, it will work any place that you can give me electricity and gravity. So a Mars MRE system would be very similar to the lunar application, except it would be, have a little bit more thermal loss due to the Martian atmosphere and convection with the atmosphere. And so we need slightly more power. If you want to power this with solar energy, we'd obviously need solar arrays roughly twice the size of what we would use for the moon. But other than that additional thermal loss and a larger solar array, MRE could easily extract metals from Martian regolith. The presence of CO2 on Mars means there's another way to do a lot easier extraction of oxygen than our technique. So I would not use our MRE process to get oxygen out of Mars, but if we do make metals, oxygen comes out as a byproduct. As for our vapor deposition process, unfortunately, it needs a high vacuum, so it would not be able to work in the Martian atmosphere. Next chart, please. This is my last chart. In summary, I really want to reiterate the potential impact that implementing FarView may have on science and lunar exploration. The ability to land a few hundred kilograms of hardware and then generate tons of useful metals and oxygen per year from the regolith without the need of anything from the Earth will enable materials to, will make available materials to build exploration and science facilities at much lower cost and risk than if everything had to be brought from Earth. Most importantly, the ability to manufacture power infrastructure components that can be used to operate facilities during both lunar day and night will enable much more than just FarView. And it will open up new pathways for exploration of the moon and beyond. As I said before, everyone needs power. Similarly for science, we'll open up a new window into the universe, protecting from Earth-generated noise. FarView will be far more sensitive than Earth-based facilities at this low frequency and provide exquisite data in a number of areas, the early universe and radio transits, exoplanets, and magnetic phenomena within the solar system. I thank you. Any questions?
Great, thank you. We do have a few questions. Our first question, will lunar dust be a problem either from charging or just coating the antennas?
The lunar dust is actually transparent at these frequencies. So yes, we expect that there will be dust, and we will, not, unless it gets really severe, it's got to be pretty thick for it to start impacting antennas. But also, one of the things we just started looking at is with the oxygen that we're generating for our rovers, there is a big issue of lunar dust. And so we're looking at basically, is there a way that we can use our extracted oxygen as the equivalent of canned air and spray it on some of the rover parts that gather dust? And our Astrobotic, our rover partner, is very interested in this and thinks this might actually be very useful. So yes, dust is going to be a problem. Thermal cycling is a problem. Charging is going to be a problem. All these, at least right now, seem very tractable.
Great, thank you. What bandwidth would you need to contact back with Earth, and how would that be relayed?
Right now, it's been an interesting evolution. When we first started this, we were looking at something like 10 terabits per hour, which would be very difficult. With a few changes, we got it down to 5 terabytes per day. And we think there are ways to reduce it even further. With 100,000 dipoles, there's no way we're going to be in a low data mode. This is going to take a lot of data. And looking at what infrastructure is likely to be there, obviously, we're going to have at least an optical comm link to either our own relay or to an infrastructure relay. But yeah, that's basically a topic for phase 2 as we map out how we're going to get all the data back.
Thank you. You talk about metal extraction to be used for electrical conductors, but what would you use for insulators and RF generator circuits?
We actually, for the receivers right now, we're looking at probably having to bring some of those components from the Earth. There are parts of it that we can make with lunar materials, but it looks like there are parts that we cannot. Can't give you a really good answer right now, but the lunar surface itself, we think should be sufficient insulation, but that's going to be a more detailed study later. For those who've had NIAC phase ones, you don't get a whole lot of resources.
Thank you. And I'm going to read this verbatim. Wouldn't this be ideal for SETI technosignature purposes?
I would think so. We've also been contacted, once information has been getting out, we now have been in contact with solar physicist group that wants to actually have us design a much lower frequency, 1 to 0.25 megahertz. And another group that wants us to design a higher frequency, a few hundred megahertz. So this is, again, a very, very easy to modify system. So if there are particular bands that people think we would look at, it's probably not going to be difficult to build one.
Great. And what are the differences of using FarView's distributed architecture versus a single large farside antenna in a crater?
Basically, we're an interferometer, so we get a lot more information. We image the whole sky. Any dish antenna will be like Arecibo. It'll image a small spot in the sky. But also because it's an interferometer, we get a lot more information on the power spectrum, which is something we can't get from a single dish.
Great, thank you. And we are out of questions. So thank you, Ronald.
Thank you.
Thanks very much. We appreciate it. And I'll repeat, as I've said for previous NIAC fellows, we hope to see you in person at the 2023 event. Thanks very much.
That would be great. I used to live in Tucson. I was at the University of Arizona.